Okay, we're going to do some sample problems relating to fluid power. First one, we have a pressure of 7.5 psig. We want to know what is the absolute pressure, psia. So all we have to do here is add atmospheric pressure to the gauge pressure to get the absolute pressure. So we add 14.7. Should get something like 22.2 psi absolute. 2, we have a pressure of negative 3.5 inches water. We need to convert this to units in psi. So we do our conversion factor. We know that an atmosphere has 14.7 psi, and an atmosphere also has 407 inches of water. So we can use that conversion factor to go between the units. So we just multiply. We get negative 0.13 psi. And this is a gauge pressure because it's measured relative to atmospheric pressure. Next, we're going to convert volume flow of 25 pounds per second. We want to convert that to cubic feet per second and gallons per minute. So we know that the density of water is 62.4 pounds per cubic foot. So this is our water flow, 25 pounds per second. Density of water is this, so that'll let us convert to cubic feet per second. So I take my 25 pounds per second, and I put 62.4 pounds per cubic foot. And I get 0.4 cubic feet per second. And then to go to gallons, 1 cubic foot of water is equal to 7.48 gallons. So if I take my 0.4 cubic feet per second, convert to gallons, 7.48. And then I got to convert my seconds to minutes because I want minutes here. So 60 seconds in a minute. That becomes about 179 GPM. And I'll do a similar one but with water, or with air instead of water. So if I have 6.6 pounds per minute of air, we want to determine the flow rate in cubic feet per second. We know that the density of air is 0.075 pounds per cubic foot. So I have 6.6 pounds per minute, and I can convert to cubic feet 0.075 pounds per cubic foot. And then again, minutes has to be converted to seconds. So I have minutes up here divided by 60 seconds. And you should get 1.47 cubic feet per second. We're going to determine the pressure in psi at the bottom of a lake, which is 33.9 feet deep. .9 feet, and we want to determine the pressure at the bottom, which is a depth of 33.9 feet. We know the density of water, 62.4 pounds per cubic foot. And we want to know the final pressure in PSI. So I take this depth of water here. Remember that feet is also a pressure unit. It's feet of water column because we're measuring water in this case. So if I have 33.9 feet, it's like saying feet of head or feet of water, and I can multiply that by density of water. And this will give me 2115 pounds per square foot, but I want pounds per square inch. So I do one more conversion. Oops, it should be squared. And I need to convert to pounds per square inch. So if I have 1 square foot, that's equal to 144 square inches. 12 times 12. And the answer is 14.7 psi. Now this is, remember, these are relative to atmospheric pressures, so these are gauge pressures. So I gave you a pressure measurement here that corresponded to atmospheric pressure, but it's just a coincidence. So if I were to convert this to absolute, it would be 29.4 psi absolute. Okay, so this is a pump problem. The pressure on the discharge side of an irrigation pump is 32 psi. And we want to know how high will the pump lift a column of water. And for this problem, we're going to assume the pipes don't have any pressure drop. So they're zero resistance pipes. So basically we need to convert this to a pressure measurement that measures height of water column. So remember, this is equal to 32 pounds per square inch. And I know the density of water is 62.4 pounds per cubic foot. So that takes care of the pounds, but I've still got square inches and cubic feet here. So I need to convert again 144 square inches in 1 square foot. Everything will cancel except for 1 feet unit. So that will give me my water column in feet. It comes out to about 74 feet. So a pump with a discharge pressure of 32 psi will lift a water column 74 feet. Okay, let's do another pump problem. We have a pump removing water from a well at the rate of 88 GPM, 88 gallons per minute. I want to convert this flow rate to cubic feet per second. So this is 88 gallons per minute. Notice I write out the units in this fractional way before I do the conversions. Just makes it easier to cancel units. So 88 gallons per minute, and I want to convert to cubic feet per second. So I need to do my minutes conversion, 60 seconds. And I have 7.48 gallons in a cubic foot of water. So this is about 0.2 cubic feet per second. Now let's say we want to know how much time will it take to remove 1200 cubic feet of water from the well. I can take that rate, multiply it by my amount, 0.2, except I have to do the reciprocal. So I put my 0.2 cubic feet down here per second, and I get a rate, or a time of 6,000 seconds, which is equal to 100 minutes, or 1 hour, 40 minutes. Okay, next we have an air changes per hour problem. So if I have an air duct that provides 12,000 CFM to a space, and the dimensions of the room are 120 feet by 65 feet by 18.5 feet. First question, how much time is needed for an air change, a complete air change? So we want to replace this entire volume of air with new air using this flow rate. So first step is find the volume of the room, and we just multiply those dimensions, and I get 144,300 cubic feet. Now I'm changing air at this rate, so I can figure out how long it takes to replace all this air with new air. So I have 144,300 cubic feet, and then I have 12,000 cubic feet per minute. This will tell me how many minutes it takes to replace all of this air. And I end up with about 12 minutes. So after 12 minutes of this airflow, all the air in the room gets changed. So the next question is, how many air changes per hour? To do that, I can figure out that basically how many of these time periods happen in 1 hour. And there are 60 minutes in an hour. Therefore, I have 5 air changes per hour. Next, we have a pump power problem. So if I have a pressure of 65 psi and a flow rate of 50 GPM, what is the output of the pump? What is the output power of the pump in horsepower? So I can use my working equation to solve this. 65 times 50 divided by 1715. Remember, these units have to be correct, so this only works for PSI and GPM. I get an output power of 1.9 horsepower. I could also call this 1.9 water horsepower. Now let's do one but for a fan. So my pressure is 1.5 inches of water, and my flow rate is 1500 CFM, and I want to know the output power of the fan. So again, I use my working equation, 1.5 times 1500 divided by 6356. And again, this equation only works for air if I have pressure measured in inches of water and flow measured in CFM. So this gives me 0.39 air horsepower. That's my output of my fan. Actually, 0.35, sorry. So the next few problems we're going to talk about combine motors with fans and pumps. And I find it always helps to draw a diagram of that type of system. So if I have a motor and I'm supplying some electrical power, I'm going to call that power in. And the motor goes to a fan. The horsepower right here between the motor and the fan is the brake horsepower, bhp. Output of the fan is air horsepower, ahp. So when the electrical power comes into the motor, we lose a little bit due to efficiency losses, and it becomes brake horsepower. That's the output of the motor, but the input to the fan. And then we lose more in the conversion of the fan because the fan has its own efficiency losses, and we get air horsepower out. So each of these devices has their own efficiencies. So if I call this the efficiency of the motor and this is the efficiency of the fan, if I multiply those together, I get the efficiency of the system. Efficiency of the motor times efficiency of the fan. So for example, if my motor and fan were both 90% efficient, my system would be 81% efficient. You just multiply those two. So when you're given these problems, try to draw a diagram like this. If it's a pump system, you replace this with a P for pump. This becomes the efficiency of the pump. And then your air horsepower changes to water horsepower. Everything else is the same. So with that in mind, let's do some examples. Let's say I've got an air handler whose power input, so that's Pn, is 3 kilowatts. The efficiency of the system is 75%. The pressure is 6.4 inches water. And we wanted to determine two things: the fluid power output of the fan system. So we want to know the air horsepower, and we want to determine the volume flow rate in CFM. P dot. So let's do the air horsepower first. I know that the efficiency of the system is the product of the efficiency of the motor and the efficiency of the fan. I don't know the two individual components, but I know the entire system's efficiency. So I can go from power in to air horsepower using the system efficiency. So I have this equation. Power out over power in is efficiency. Air horsepower or Pn. Of course, you have to do appropriate unit conversions. So if I take 75% of 3 kW, that gives me 2.25 kW, which I need to convert to horsepower. So I divide by 0.746. Because there's 0.746 kW per horsepower. So that gives me an air horsepower of 3.0. Notice that's the number is equal to the kilowatt number here, but that's just a coincidence because our efficiency happened to be very close to the conversion factor between kilowatts and horsepower. So don't assume that we can just flip the units to horsepower. It's going to depend on the efficiency. Okay, so that's our output power, and I want to know volume flow given this much pressure drop. So we're going to use our working equation. air horsepower equals delta P times volume flow divided by 6356. I know the air horsepower is 3. I know the delta P is 6.4, and it's in the proper units, inches of water, for this air system. So if I solve this equation for V dot, I will get the volume flow in CFM. If I do that, I will get approximately 2980 CFM. So notice in this particular example, I didn't know anything about the brake horsepower or the motor efficiency or the fan efficiency. I went directly from power in to air horsepower using the efficiency of the entire system. Now I want to point out that sometimes these problems discuss the motor and the drive as separate components. So here's the drive. And this could be a pulley system or something like that, a belt. But we consider the brake horsepower to be the output of the drive in that case. This is still the air horsepower. And this is still the power in. So when you see problems like this, they may have three efficiencies: the efficiency of the motor, efficiency of the drive, efficiency of the fan. But still, the system efficiency is the product of all of these components. Most of the time, though, we consider the motor and the drive to be one unit, and we just consider the efficiency of the motor system.